So what are now the constituents of a mathematical model? We distinguish three types of constituents: the variables, constants, and the parameters. Within the variables, we have the input variables. So basically, those are the quantities that will influence our outcome and the one that we will measure. Inputs, they usually depend on the state variable. So they depend on the location given by the space coordinates and the time at which they are taken. And then finally, you have the output variable. So the quantity of interest that we are trying to model in function of the input variables. Constants are usually physical constants, biological constants, gravity, constant of Euler, all those kinds of things are the constants. So they are not changing over time of over location. And then you have the parameters. So parameters are the things that we are interested in that we will want to estimate. So these are quantities whose value can change depending on the application. So they determine how much each variable contributes in the final model. Parameters, examples of parameters are the slope and the intercept in the linear model, so the one we saw in linear regression. Quantities that depend on environmental conditions such as temperature and pressure, they are characterized by parameters, decay rates, and so on. One thing that's important is basically to go from an input to an output that will be done through the mathematical equation. So we can have analytical, where you have y is ax plus b, for example. You can have ordinary differential equations of the type ds dt is some fs minus k times s, or you can also have partial differential equations, where, for example, you could have the heat equation delta u over delta t, or delta u delta t, is alpha times the second derivative to each of the coordinates. And so in this case, here, you see that u, this one depends on x, y, z, so on the coordinates of the location and on the time. So u is the variable, x, y, z, and t are the state variables in this case. Data types, so we can have three types of data. The easiest one is deterministic. Deterministic data are exactly known, there is no variability in it. It's just a fixed value, which is usually the case for a constant. You have stochastic variables. Stochastic variables are the variables that we saw also in statistics. They are associated with a probability density function, so different values have a different probability of appearing, which leads to uncertainty in the data. Uncertainty in the data characterized by this probability density function, and so this variability has to be taken into account in the data. And then the third one, what is new in this case, are fuzzy variables. We will not use them, but I will explain them anyway so you have an idea about what they are. So if we make plots, the deterministic variable is easy, left up, upper left. It's just a fixed value for x, so x is my variable. It has one value, so it's deterministic. On the other hand, if x has a certain probability density function, we call it stochastic, upper right one. Fuzzy variables are a bit different in the sense that they are neither deterministic nor stochastic, but they are also not fixed. So here we do not work with PDFs, but we work with membership functions. So at any given time, every value of the variable can be in one or more membership functions. So if we look at the example and assume that the variable is the water temperature, we could distinguish three types: cold, lukewarm water, and hot water. But cold, lukewarm, and hot will depend on the person as well. So not everyone has the same definition of cold. Not everyone has the same definition of hot. So we define membership functions in such a way that every point here on the x-axis is always part of at least one membership function, and the sum is always 1. So if you look at the different values, so for the membership function, they sum up to 1. Basically, there are probabilities to be in that membership function. So if you look, if this is, for example, 1 degree Celsius, 1 degree Celsius, what we see here, is characterized by everyone as cold. So the value of the membership function is 1, because with 100% probability, 1 degree Celsius is given as cold. Same thing if this would be a water temperature of 20, it's for everyone lukewarm. Suppose that we have a temperature of 35 degrees, sort of. In this case, if we look at it, we have some people who think it is hot, some people who think it is lukewarm. And so there is a probability, more people think that it's lukewarm, which would be approximately, let's say, 0.65 and 0.35. So 65% of probability of 65% says that it is warm, 35% probability says that 35 degrees is hot. So it's not a fixed value for 35 degrees, but it's one of the membership functions with a certain probability. Also between models, we can make a distinction between deterministic models and stochastical models. So a deterministic model basically can make exact predictions. So based on the current state of the model, of the knowledge that we have, the model structure, the parameters, we can make an exact prediction without any uncertainty, because it is a deterministic model, because it's a fixed model. It's a very simple model, but it is very unrealistic. So what we will have are stochastical models. A stochastic model, just like a stochastic variable, will include some variability. And because of this variability, you will have uncertainty, which is then characterized by being the prediction uncertain. So you will have a confidence band around the prediction. So instead of just having a fixed prediction, you will have a confidence band around it with values, for example, 95% confidence band, which corresponds sort of to confidence intervals. So future behavior will be in a certain band, in a certain range. It is not a fixed value, so we are not certain about what the outcome will be, given certain input variables, given certain state variables, but we can make a prediction and we can say, well, with this prediction we have a certain confidence interval, a certain confidence band, where 95% of the predictions will lie. Model building can be sort of written like this. So you have your system. With the system you do experiments, basically what we did in statistics, to get to experimental data. That's the one thing. On the other hand, you look at physical laws, you look at assumptions to make the model. So this is the mathematical model. These are the data set, or this is the data set. And you will combine those to go to certain parameter estimation. So parameter estimation, a first estimate gives you the initial model. So you have an initial value of the parameter estimates, giving you an initial model. And then you will validate the model. So you will check, is the model a realistic model? Yes or no. If it is realistic, fine, great, you have your final model. If not, then you move back into the blue borders. Basically, you will re-evaluate the model. And this re-evaluation can be anything that you want. You can keep the model, change the variables, change the parameters, make measurements of other variables, or you can even completely change the model structure. Also very important is the goal of model building. So just as in statistics with testing, you have to define the goal before you build the model. Because depending on the goal, you will make your model, you will create a model in or on different levels or different ways. So the main purpose can be accuracy of the model. It can be fulfilling some boundary conditions, determining what is the important variable and which are less important. So depending on what you want to get out of the model building may differ. It's a very important thing that you set your goal, because it is responsible or partially responsibility for the complexity of the model that you will allow. So if you think back at linear regression, we said that if we want to make predictions with the model, it is good to have a predictive model. So we want a high R squared. If you want to look for confounding or explanation, so you look at the biological explanation behind the model, then you're not looking at the R squared, but you just try to include as many variables as possible to avoid confounding or to adjust for confounding. So depending on the goal, also there you had two different ways of model building. Same here, depending on the goal, you will differ, your strategy of model building will differ. So it's often forgotten or not clearly defined. In that case, you can end up with a worthless model. So it can be a model which is too simple for the task you want it to perform or too complex. And basically you spend a lot of time and spend a lot of money on making a model that will not be useful in real life. So make sure that you define your goal and then you act towards that goal. Model building, model selection is another thing that we have to do. So once you have an idea, you can have different kinds of models and you have to select one of them. Candidate models are based on your experimental data. So based on the experiments that you did, you could have different ideas for a model. On knowledge, so if there has been some models before on this topic, you can reuse them. So you don't have to reinvent the wheel again, but use the knowledge that exists. Creativity, you had a certain creative mind. You had a model which you thought this would be the model. Well, it all can give you certain models, and you get in the end a number of candidate models, and then you want to select one of them to present to apply. So to choose which one, you will have again a trade-off. Trade-off between goodness of fit and model complexity. So goodness of fit basically just means that it is a well-fitting the data, so fits the data points very well, which means that if you have certain data points, your model will pass very closely along those data points. The model complexity, on the other hand, is how complex is the model. So if complexity increases, you will usually have lots of parameters. And so you will have to estimate all those parameters. And the more parameters you have in a model, the less accurate each of the estimates becomes because you only have your data set that you can use. So the more you have to estimate with the same data set, the less accurate your estimates will be. And so what you would like is having a high goodness of fit, so a very good goodness of fit, very well fitting data, and a low complexity. But you can never have both. So it is a trade-off, the same as variance and bias trade-off in statistics. The variance corresponds to the model complexity here, the bias is the goodness of fit. And so the more complex the model is, the more curvature there can be in the model, and so the better they will fit the data points. The less complex the model is, so the least complex model you can get is a linear model. There the data will be fitted, well, worst basically. And so you see that if you increase the model complexity, you will increase the goodness of fit. But basically you want to have a low complexity with a high goodness of fit, and so that's not possible. So you will have to find a balance between both of them. What you can also do, if it's necessary, you can look at the model and reduce the model. So it means that I have an idea of the model, but it is too complex, and then I will take out certain parts. I can take out the variables. So if you look at variables, some of them will make for a fast convergence, some of them will make for a slow convergence. Remove the ones which have a slow convergence. If you have equations, not every equation will contribute a lot to the output. Take out the equations which have a very, very little contribution. Parameters, same thing. Eliminate parameters which have the least effect on the system, so which have the smallest variation, because whatever you do with that parameter, it will hardly change the output at all. So you have very little flexibility if a parameter has a very small variation. And you want to have a large flexibility to be able to get your model as good as possible. Model building parameter estimation is another thing that we will have to do with the model. So we will have to estimate the parameters. Basically find the optimal parameters for the model. So you will use the data, you will use the data set that you collected, and then you want to determine a unique set of parameters. So that's important. You want the set of parameters to be unique, to have a single solution that is the best fit for the data. How do you do this? You minimize an objective function. So you will get some objective function which we will call J, which will depend on the parameters, which will depend on the variables, and then you look for the minimum of this one. That data is indeed the parameters. And so your objective function will be, or will often be, a combination of goodness of fit and complexity. And so you want to find the values of the parameters which makes this objective function minimal, so which have, given the options that you have, which has a goodness of fit which is as high as possible and a complexity which is as low as possible. Sometimes this can be done in a one-step procedure. Basically, if you have an analytical solution, so if you have an equation that you can solve manually or with a computer, but you can't solve it exactly, you get in one step a solution, least squares regression, for example. Other times, most often, it will be done iteratively. So you start with initial parameters, which you get from experience, from literature, from the data. So you get initial parameters which you think which are close to the optimal solution. You simulate the model, you see how large or how small is my objective function, and how can I improve it. So I quantify the difference between the experimental output, simulated output, and then I want to try to minimize this difference. I refine my parameters and I start over again until I get to a certain level of goodness, so a certain stopping criterion. At a certain moment you will have to say, okay, this is close enough to the optimal solution. I now stop with my optimization. And then you will have, after you estimated the parameters, you will have to validate the model. So you will have to see, is my model a good model in real life? So because what happened, you use, well, basically you have your data set, you create a model, which means that the model that you created here is good for the data set that you used, but is it also generalizable? So will it also be a good model for any other data? So is it a good model in real life, or is it just a good model for the data that I used to create the model? Because I optimize my model based on the data set, it will always be as good as possible a model for those data, but that doesn't necessarily mean that it's also a good model in reality. So it can be that my data set is not very representative, or there's a problem, and my model does not work in reality. So what you have to do is you have to confront the model with an independent data set and see if it is still performing well. If it's well, then we have a validated model. So in that case, we can implement the model in real life. If it's not, you have to return to the previous steps and then either improve the data and remake the model, or improve the construction, the structure of the model. How do we do it in practice? Often you have your data and you will split it in, on the one hand, a test set, which comprises about 2/3 of your data, and on the other hand, a validation set with the other half, with the other third. So the test set is made for, or is used for constructing the model. You build the model based on the test set, and then you use the validation set to see if the model performs well on other data. Because you split before you make the model, test and validation set are independent, and you can use this ID to have, with one data set, a model created and validated at the same time. Well, in two different steps, but from the same data set. So what we will do in this part, in the simulation of biosystems, so part 1 was the creation of the mathematical model, other course. Part 2, simulation of biosystems. We will compare with the experimental data, so we will make a parameter estimation. So we want to see what are the best values for the parameters. Then we will look at simulating the model a number of times under different settings to see what happens if you perturb a parameter, local sensitivity. So how sensitive is my model to influences from the certain parameter, or how sensitive is it globally, so deterministic versus stochastic models. We will look at different candidate models and see how to select them, so choose between the candidates through model selection, and then in the end we will combine all those techniques to go to optimal experimental design. So we want to see what is the optimal experimental design for either parameter estimation or for model selection.